Hello, hello. Am I audible? Hello, hello.
Yes, sir, audible, sir.
So did you get the link for today's class?
Yes, sir, I got a mail and also it is there in the announcement page.
Okay. And what was the timing there?
7 to 9.
Okay, okay. So you are a student?
Yes, sir.
Okay. Let me see how many people will join, then we'll start. We should wait for a few minutes.
Okay, sir. Sir, I have a question regarding last live session.
Yes, please ask.
Sir, in that one question was discussed, assignment 10, question number 1.
Okay.
So I think in that even professor also what was told is like option B is the correct answer.
Uh-huh.
But actually the question asked which of the option is not true.
Uh-huh.
So as per the solution it was given is A, and A is the correct answer because that is not true. All remaining 3 options are true.
Okay.
But I think maybe due to some misunderstanding, like option B is treated as right, and they were discussing like it should be immediately notified to NPTEL to correct.
Okay.
So I already put that remark in the our discussion forum, but no response so far for that. So
Okay,
please
maybe
note
they
it, sir.
will respond. Yeah. Sure. Okay. I think they will respond, but wait for some time and then check again. So when is your exam?
So mine is on 29th.
Mine is also 29th, sir.
Okay. At what time?
Afternoon session, sir, for me.
Afternoon. For me also afternoon.
Is it online, right?
Yes, sir.
Yes, sir.
And did they give any information regarding the pattern, like whether it would be a objective or the subjective?
No, sir.
No. Okay.
It was mentioned as like online based, computer based test, because there were 2 modes only mentioned, paper based test and computer based test.
Okay.
And this was mentioned as computer based test.
Okay.
Whether we'll get, sir, like, because whatever previous course I attended, there was a explanation given, like this will be like mostly like similar to assignments.
Yeah, like that. Yes.
Sir, then one more doubt regarding the credit transfer procedure, sir.
Okay.
So whether that should be initiated through our university or through NPTEL?
No. I think when the NPTEL give you the certificate, then I think from university you have to talk that I have completed this course and this is the certificate. Now they will proceed only. I think
Okay.
NPTEL will not. They will only give you the certificate.
Okay, sir. Okay.
Yes.
Excuse me, sir. Will you
Yes.
be discuss last 2 week or for the last 2 week course only? You will be discussing problem or all the week for all the weeks you will be discussing problem today.
I mean, it's on you. I mean, I will just discuss. I will try to discuss overall what we have done and just like a overview. But if you
Uh,
want something more specific, then we can also discuss.
yes, sir. That will be highly useful for us. Please, you can recollect all the problems today. If it is mean, it will be highly helpful to attend in the next week for us. That's why.
Okay.
Are you waiting for all the participants to come?
Yes, I'm little bit waiting. Maybe 5 more minutes
Okay.
will wait because
Okay.
otherwise that would be
For
benefit.
my friends also wait, known that I'll be intimating them. I'll be complex. Okay.
Yeah. What?
I will invite my friends and I will come back soon in the same link because they also want this problem session to cover all the week courses problems.
Okay. Okay. Fine. Fine.
Okay, I'll be come back.
Yes. Hello.
Hello, sir.
Yeah, I think she's not coming. Seems.
Oh,
I don't know, but she told. Okay, let's start.
okay, sir.
Can you see the slides?
Yes, sir. Visible now.
So this will try to summarize, this and
Okay, sir.
see how what can we just, yeah, so it will be just go through session kind of. Okay. Yeah. So initial what from where we have started in our week green is the something revision on optics, resolution, magnification. So this is very simple like resolution. So what is resolution like? Where you can see the two entities very clearly, without any mixture. So this can be, you can see these 2 points separately. Okay, so this is your resolution. In the resolution, then it comes the depth of field. This formula you should be very well noted down that r is d1 by 2. It is nothing but 0.61 lambda upon mu sine alpha. Okay, and So this formula based question can be asked in UNESCO exam to find out the depth of field, to find the resolution, to find the alpha, or to find the mu value. Okay.
Okay, sir. Sir,
Then
here D1 is the distance between the points, huh?
uh,
Or
okay, D1 is your this yeah, this is the distance between the point. Like here, this is your just a second. Yeah, it is written somewhere now. Yes, that is that. The depth of field is very different from the resolution. So this R is your resolution, okay, and that is your point. So which is nothing but 0.61. Lambda is your wavelength.
wavelength? Okay.
Yes. This D is your depth of field. Okay.
Okay.
Now we covered the various kinds of basics of the your microscopy, like transmission electron microscopy, scanning electron microscopy, optical microscopy, AFM. So here, if you remember, I explained all this kind of a microscopy in the very beginning. So it is asking the TEM is similar to what? So I have explained from the optics, it is similar to the optical, right?
Sir, AFM, can you please brief, sir?
AFM is nothing but atomic force microscopy to detect the. Just a second. AFM here, that will be actually that is not in your syllabus anyhow. But for
Yes, sir.
your this thing, AFM is like there will be a piezoelectric tip, and that will scan your surface to know the surface roughness, whether it is a smooth surface or whether your surface is rough, very high roughness. So in this way, you can um, capture the surface morphology of your samples.
Okay.
Okay.
Okay, sir.
After that, we did this optics somehow, that how the image is forming, some illumination system from where the light source, the light is coming, how the lenses are, placed, and then how the image is forming. Then we studied little bit about the Rayleigh criteria, where we discussed that how this, I mean, when the iridescent pattern is formed, then what should be its intensity. So if you remember, the central spot is much more intense than the other. Okay, so it contains overall 84% of the light intensity, if you remember. Now, the relay criteria, what it discuss? So it discuss when the maximum of intensity of iridescence coincide the first minimum of the second, the 2 points can just be distinguished. I mean, this is just saying that how what is the condition when the 2 point can be distinguished. So it says about that. Okay, I mean
Okay.
how it is showing the correlation, that how it can be distinguished between the 2 points. After that, we studied about the numerical aperture. Numerical aperture is this given by this, which is nothing but it is referred to in terms of semi-angle alpha, which is the subject, and this also you can calculate by this formula. So the product mu sin alpha is called numerical aperture. So when they will tell you to calculate the numerical aperture, this you have to calculate the mu sin alpha. After that, we discussed about the how can we improve the resolution here. So I have given you that how can you improve the resolution like that. So uh, here you can see if you want to increase the resolution, how you have to vary the alpha and the lambda value in order to so here the best resolution is possible when you have to decrease the lambda or
Lambda,
increase the mu or
mu,
alpha.
and alpha.
Yes. So this can be asked. After that, aberration, there are so many kind of it is like what we have studied in our 9 or 10 chromatic, monochromatic aberrations and all. Just Yeah, so after that we discussed about yeah, this is the basics, distortion and all, how your image will look and what are the causes and how can you, rectify this kind of a distortion, and what could be the reason to, have this kind of a distortion, how this geometry or image can be distorted. And after that we did some numerical like this. So just now I have discussed, here you have to calculate the resolution. They will give you the lambda, mu value and the alpha value. After that, we discuss about how the system, which is nothing but your how it has, in the optical microscope, how this all the lenses and I mean systems, how they all have arranged systematically, and how the image formation take place. And then we discuss, yeah, this is again the same thing. And yeah, so there are in the microscopy, there are like different kinds of a microscopy, reflected light microscopy. So we have discussed about that for what reason we use this, and what are the arrangements in this kind of a microscopy. Then there is another one which is nothing but a transmitted light microscopy. So in reflected, the basic concept is reflection. Here the light is not transmitting, and but in the transmitted, the light is transmit. So that's why here we use the immersion oil, to impact on the refractive index, and also the light will transmit to illuminate onto the surface of the sample, and it will go through the sample. Now, the one thing which I would like to say that, yeah, contrast. So contrast is what? Contrast is nothing but the intensity of the surface minus the intensity of the background divided by the intensity of your background. Okay, so this is your contrast. So contrast is also depend on the background intensity. Okay, so here when you will see the background intensity, this is the background intensity. So the background intensity is here, it is increasing, so your contrast is decreasing. Okay, so this is the formula for your contrast, percentage of contrast. And yeah, so here you can see the contrast difference. This is captured by your bright field illumination, this is captured by your dark field illumination samples. And yeah, so you can see better in the dark field illumination samples. Contrast comes from the light scattered by the samples. And yeah, this is again the same one. Yeah, so this will told you about the phase contrast imaging of the transparent thin specimen. So here what we will have, this is your cells, and when the light will come, so this is the phase contrast, make this tiny difference because of in the refractive indices visible by the use of the optical manipulation. And here it translates them into the difference in intensity that can be visually observed and the recorded. So here basically there is a phase difference. Okay, because of a different refractive indices. Here you can see refractive indices is different, here it is different, so that's why you can get a contrast. So example of this phase contrast optical microscopy. So here you can see in the phase contrast, you can easily see your living cells in the bright field and the contrast mode. After that, we studied the halo and the shadow of artifacts. So here you can see here also, because of a difference in the refractive indices on the phase contrast is excellent and method to increase the contrast when viewing or imaging the living cells in culture, but typically results in halos surroundings the outline of the features. So here you can see this is the outline kind of things, you can see like a shadowing effect. And it is because of the configurational parameters of the phase contrast microscope optical system. Yeah, and this occurred in the phase contrast microscope itself. We also studied about this DIC. So where you put your DIC, and the polarizers, a little bit about the prisms, Wollaston prisms, Nomansky prism, how can you use that, and this is about the Wollaston prism. And depth perception, we also studied the depth perception. Here you can see, if you want, this is your image and this is your depth perception. So how by using this DIC mode you can get a depth perception. This need to be remembered. In the DIC mode only you can get this kind of a depth perception image. And yeah, this is about the polarizer. So here you can see how you have to place your polarizers in order to in order to get the image, or the where like a first polarizer is placed beneath the sample trace, another polarizer or placed above the objective lens. So in this configuration, the polarizer and the analyzer are crossed with no light passing through the optical system and dark background present in the eyepiece. This is the same. Yeah, this is the lambda plate. It is also having, if you have a different kind of a phases in your sample, so in order to, because of the part difference leads to an extension of certain wavelengths in the light for the interference, so you will get a very beautiful color picture of your samples. This is again Voight has used for the face identification by reflected this microscopy, polarized microscopy. So yeah, if your sample is having a different face, like your tetragonal face or the orthorhombic face, so that you can distinguish by using this kind of a microscope very easily. So yeah, this is a phosphorescence. So phosphorescence is nothing but, okay, this is your ground state. So when you excite an electron, it will go to the excited state, and there is a triple state. So there is a possibility when it can come from the excited state to the ground state. This is nothing but the fluorescence, but this is the intermediate state. When it will come to the intermediate, and from the intermediate state, when it will come to the ground state, it will give the phosphorescence because of the difference in the energy levels. This is fluorescence versus phosphorescence. So this is your fluorescence. Just keep in mind that what is the range of this. This is the 10 is to power 10 to 10 is to power 7 per second frequency, and the 10 is to power 5 to 10 is to power 3 per second. Okay. This is less because it is having a less energy difference. This is more. Then we discussed about conduction band, outer cell electrons. Yeah, hello. Did you ask your friends to join?
Yes, sir. She will join soon. After within 5 minutes, she will come back, sir. She'll coming. She'll be coming.
Oh,
I joined. Yes, sir. Sir, Asen, are you discussing which? Sorry, I want to know that for which week you are discussing the problem?
I'm just summarizing that what we have done so far, so that it would be a good for you to,
Yes, sir. Yes, sir. Yes, sir.
yeah.
Sir, I'm not disturbing you, but I want to know that Rayleigh criterion resolution factor, that is R equal to 0.61 lambda divided by mu sine alpha. That is formula for resolution. It is given in assignment 1.
Yes.
Yes. R equal to 0.61 lambda divided by mu sine alpha.
Yeah.
Their resolution increased by decreasing wavelength, they are saying. So how?
Yes, yes.
Because left hand side is resolution.
Yeah.
If
So
it is
see,
directly proportional means,
no,
if
no.
it is increasing, yeah.
See, what is actually you were not
R should be lower for better resolution.
Yes, yes. So you have to know that resolution. So if I would say a better resolution, okay. So better resolution, it means to say the R value should be low. Then only your resolution will be better. So how
Yes.
the R value will be low? When you will decrease the lambda, right?
Fine, fine. Okay, so resolution means that value should be low. That for that reason only wavelength should be low and
Yes.
this one
Yes.
increasing refractive index. That is
Yes. Yes. Yes.
okay, sir. Okay, sir, you can continue now.
Oh. So then we discussed about this EM, a little bit about the outer electrons, how it is situated, and like your quantum number, your quantum cells, KLMN, and how what and when we you I mean what are the energy required to knock out the electrons from the different cells. Okay, and then in the electron microscope, it's very important to have electron source. So there are many kinds of, not many, like basically in our course we have studied like a thermo emission and one more. So here this is about the thermionic emission. So here when you will heat a particular, when you will apply voltage, it will heat, and after a particular threshold well voltage, your electrons will come. Okay, so after that. Yeah, so this is your thermionic gun. So this is the how it has placed. So this is nothing but, yeah, just keep in remember they can ask like electron guns which use lanthanum boride LaB6 are quite common on microscope and used for the high resolution work, since in both of these fields are light brightness is desirable. So this is your lanthanum boride, and this is nothing but a single crystal of LaB6. Okay, so just keep in mind this is single crystal. Field emission and thermoionic, two kinds of electron gun. Now this is your, yeah, this is your filament current when you are when you will get a current. So here firstly what will happen, uh, as the current through the filament is split, there is an initial rise in the emitted electron beam current. Okay, and after eventually after a certain period of time, it will getting start saturating, and there is no point in passing more than critical current. Okay, so you should know that how much filament current you should give. So after this you can't give because there is no any increment in the beam current. Yeah, so this is again the same thing. This is a factual, or I would rather say something to remember, that about something like what should be the size of your point, and how it is better than the others. And this is your FEG. So this is also the same thing. And no, uh, yeah, this is this week basically most of things are like something to kind of a remember, or something you have to yeah, keep in mind, like that. No any rocket science is there. So that there is, after that we discuss the scattering, like the elastic scattering or the inelastic scattering. So here there is a when your incident electron is coming and it is deviated completely 180 degree without losing its kinetic energy, then that is your elastic scattering. And when they will interact and deviate, so there is a lose in the energy. So that is your inelastic scattering or your inelastic interaction. So here when you will see, so when your incident will electron beam will have inelastic interaction, then there will be a so many things will come out from your samples that we will see in our further, that what are those things. Yeah,
Sir,
so
excuse me, sir. Can you tell something about agar electrons?
yeah, I will tell. It will come in a. So auger
Okay,
electron
sir.
is basically nothing but when your incident electron beam is coming and interacting with the specimen. So when it is interacting very near to your surface, very near to your surface, then the electron which is getting knocked out from the surface, that is nothing but your auger electron. But when your incident electron beam is having a high kinetic energy, and when it will interact to a very depth, or the more depth in your surface, then it would be a morely like a secondary electron or your characteristic X-ray kind of. Okay,
Okay, sir.
yeah. So in other electron is basically the thing is that it has to be come from the surface. Now the mean free path is, you know what, I mean to say, a path which is related to scattering. I mean, how, or I should say, electron in average interacts two times within the distance. Okay, how many times it has interact before the collision. Okay, how distance it has covered before the interaction or the collision.
What is the QT, sir, in that formula?
Okay. So in this formula, it has which one you are saying?
Sir, this lambda MFP is equal to 1 by
Yeah.
QT is given now. So
Yes. So it has coming from, I think, previous slide. Just let me. Yeah. So mean free path is related to the scattering cross section. So this Q is, I think,
okay, interaction volume. Maybe
yes,
that process.
yes. I think I have not written this. Okay, I note it down. Then this is again, yeah, some simulation or the probability or the regarding it is concept of the interaction volume. So yeah, so this is your interaction volume. So somebody was asking that the other electron. So you can see when the electron beam is coming and interacting from the very surface, the electron is coming, or the, so other electron. Why it has used to determine the surface atomic compositions. After a depth, this depth, secondary electron will come. Why it has used up to 100 nanometer to analyze the topographical information. After that, your backscatter electron will come up to till 500 nanometers. So why it has used to determine the atomic number and the phase difference. After that, your this characteristics X-ray come 1 to 3 micrometer to determine the thickness atomic composition. After that, your continuous X-ray will come, or the Bremsstrahlung long X-ray will come from 1 to 4 micrometer. And after that, your cathodoluminescence will come to tell you about the electronic state information from 1 to 5 micrometer. So these are the things coming, signals are coming from the different depth of your samples when the electron beam is interacting. Okay, so this is again the same thing about the interaction of your electrons. Okay, so this is a Monte Carlo simulation. So this is earlier image I have shown you on a very I should say the quiche or the very well manner of your interaction volume, but in a reality that is not always like that. So when it has simulated, so it will something coming like this. So what they did, they just show them like that. So after that, this is, yeah, this is very important that you have to keep in mind that what is the effect of your when the atomic number is increasing, and this is your energy. Okay, so you have to know. So just a second. Yeah, so this is the question like that. The size of the interaction volume and the penetration depth of the electron increases with increasing the electron energy or decrease with the atomic number. So how your interaction volume is increasing or decreasing when you are increasing the atomic number or increasing the voltage. So this kind of a things we should keep in mind. These questions can be asked, so you should know the relation. Okay, so just go through it. Like this is very simple and there is nothing to explain much. Yeah, so this is your contrast generation in your electron microscopy. Here you can see how you can distinguish between this where you want to focus and the background. So this is nothing but I think your gold nanoparticle or something in your TiO2 catalyst. So this is a mass contrast and another one thickness contrast to show the difference in the higher mass and the lower mass, and the your high thickness and the low thickness. After that, this is a bright field, and here you can see like how which will appear brighter and why, because of a mass and the thickness contrast. So this is also very good and important concepts like aluminum and the copper that they can ask. Okay, now after that a little bit about the SAT pattern. So this you can go through by yourself. I think this is just an arrangement, one extra set that we usually insert in the system. Electron diffraction pattern. So this is like how you are creating the diffraction pattern. So these are the different from where you can get to know that what kind of a crystal it is. So this you can usually get from the electron diffraction pattern. So it is nothing but a special distribution of the scattered electrons. And when you will, there will be scattering of the electrons, so the intensity at the very center is very higher, and now after that the intensity started to decrease in this manner. So there are a three kind of usually material: crystalline, polycrystalline, and the amorphous. Crystalline is very well arranged atoms. Polycrystalline means the one set of arranged in one manner, and then another set of atoms are arranged in another manner. So there are a different kind of a setups. In amorphous, there is no any random arrangement. These all are the very randoms. Okay. So this is also depends on how what is your materials in nature, crystalline, polycrystalline, and on the basis of that you would have this interaction of your incident electron beam and how the diffraction is occurring. So after that, this is very important. Please do read this concept, the Bragg's law. Bragg's law is very simple. So there will be your different interatomic planes, and your incident incident beam is coming, and this is your diffracted beam. So this is a very simple formula. Keep in mind, and lambda equals to 2 pi sine theta. One numerical definitely they can ask to determine the lambda or the theta. So this is d is nothing but your interatomic or the interplanar distance, and theta is your this angle between this, and lambda is your the wavelength of the beam that you are using. Okay. Now after that your yeah, this zonal plane, zonal axis can be asked. There's what is and how can you determine. So this is the formula of the zonal axis: LUW HUKV plus LW equals to 0. HKL is your zonal plane. Okay, UVW is your zonal axis. So how you will, if they will give you the U or you can say, let's say, a KL HKL zonal plane, how you will calculate the UVW zonal axis? So you just have to create this determine. Okay. Yeah, so this is a formula for that diffraction pattern and the real lattice. R equals to constant. This is again the after the contrast, in the series of the contrast there is a diffraction contrast. So there is also a bright field and the dark field. So because of it, sample is crystalline, then the diffraction contrast appears in the bright field and dark field TM and dash TM images, and only a few electron passes such areas without any interaction, and therefore dark contrast appears in the bright field image. So this is about theory part that you have to read. This is again the same. Not very important. Uh, yeah, this is important, like a diffraction pattern for the polycrystal. So here you can see the ring diffraction pattern from a polycrystalline pure gold film with FCC crystal structure is forming. So here, because of d values and thus the distance in reciprocal space are the same, the spots are then located on the ring. So here this is like different of this diameter is coming in the polycrystalline. So this is a single crystal versus polycrystalline. So this is the resolution on in the percentage. So single crystal diffraction, an arranged event in which the crystal and the incident X-ray beam must be configured so that the Bragg's law is satisfied and the diffraction will occur in single crystal diffraction. In powder size specimens, such orientation is not essential for the diffraction, but in single crystal it is required. Yeah, so this is dark field imaging. So there is a two kind of us. So read that how the dark field imaging and what is the bright field imaging. So and how the systems are arranged, and suppose let's say here you can see a difference in the bright field image and the dark field image. What could be the difference, and you can identify from here that they can simply ask on a very basic level. Okay, so in this I have noticed one thing. Yeah, this is a very basics about the evolved sphere to just to electron valence is just inversely proportional, nothing. Yeah, this structure factor is very important. So you have to keep in mind the selection rule. So for the FCC, BCC, SCC, SCP, what is the allowed reflection and the forbidden reflection? Okay. For an example, yes. So in FCC, you can see the HKL are all odd or all even, or for the forbidden reflection, HKL are mixed odd or even. Okay, so that you have to remember these things. You have, I mean, there is no any something. These are something which has already proven by this crystal structure and all the things which we have discussed. So that this can be directly asked questions. So without wasting your time, you can answer this kind of a questions. So yeah, dislocation is also kind of a defect. So in TM you can observe a dislocation. So yeah, this is your dislocation and how it has formed. Here you can see these are the different dislocations image. Yeah, in SCM we have discussed regarding how the scanning mode works. So in the scanning electron microscopy, in the scanning electron microscopy, usually it scan in the raster scan manner by the X and Y, and it will give you the image of a better resolution. Uh, and the secondary electrons, and that you have to also remember it is a low energy or the high energy or elastic or the inelastic scattering, just like from where it is coming. For non-scattering is also because of this how vibration, how it has been created, and this is the inner shell excitation. It is nothing but when your electron beam is coming, and so from where it is interacting and how the electron from the higher energy state are filling the vacant position or the vacant place of the inner cell electrons. Just a second. Yeah, so after that, yeah, so this is again the same thing, the electron interaction volume. And yeah, in the secondary electron also there are different mode, Se1, Se2, Se3, Se4, that you have to know that why it is distinguish what are the reason, because of its trajectories are different when it interacts with the samples. uh, After that, we studied the backscattered electron. So backscattered is also it is elastic scattering. So when it is coming and it will deviate completely from the effect of the nucleus, then it is backscattered electron. So this is more or less similar kind of a thing which we are repeating. Only the questions that they are asking is different, just depending on the concepts how it is clear. Yeah, so X-ray detector, there are different kinds of detectors which observe or which get the particular signals, like X-ray, so that will detect the X-ray signals. Secondary electrons, so where the secondary electrons will go, and that will form an image or give you the information that what is required. Now, yeah, detecting backscatter, yeah, this is the same thing. Yeah. This is how the real image looks, and this is your secondary electron detector. This is your ADX detector, and this from where the electron beam is coming. This here is your BSC detector, backscatter electron. So there are different detectors which will detect the particular signals. So they have their particular arrangements. Yeah, depth of field, that is kind of a numerical. You have to keep in remember h equals to 2s into wd. So here you can see this is your aperture plane of optimum focus. So this is your alpha, which is angle, and here h is what, s upon ma. So m is magnification and s is your display pixel size that they will give, and convergence angle is given by your this. This is working distance, I think. Yeah. So there is also, they have given you the examples that how you have the depth of field has been calculated. So for SCM, is your 100 micrometer. Working distance is your, this is A is your aperture diameter. This is your working distance. This is your magnification and the depth of field. So that they can ask, just you have to put in the formula 2S into WD divided by A into M. M is your magnification that they will provide. So this is the why you are using a large depth of field in your SCM. So yeah, again the theoretical questions. EDS has like there are different kinds of a detector. ET detector is what they can ask the full form. Everett Hart Thornley detector, in lens detector, silicon detector, both ET and in lens detector. So I read little bit about the detectors also, and how they are, why they are using basically in that particular uh, thing. After that, we discussed, yeah, this is the same thing, like how contaminant from a specimen chamber in EDS detector is made, and this is about how they have made. They are just asking. This is about the EDS detector again. This is the numerical. This is about the EDS detector again. So these are the basic theory that you have to read it. This is the WDS, like EDS also. This is a WDS detector.
Excuse me, sir.
Yes.
Sorry for the interruption. In EDS, sir, there is one assignment question was that in EDS, number of EHPs can be calculated by adding it that one with 1,000. Why we are adding the quantity with 1,000 and we are dividing it by the energy. Energy, okay, 3.8 is constant.
What you said?
The number of electron hole pairs can be calculated using
Yes,
the
yes, yes,
relation.
yes, yes, yes. So I think that somewhere I discussed. Yeah, this is na.
Yeah.
Yes, yes, yes. So that I think I have discussed, and also in the class I have given some formula that time. Did you attended that class?
No, sir, because I didn't enter that problem solving sessions. Almost I missed all those classes.
Why?
Uh, uh, because I'm doing PhD, so I am doing for part time. I'm just entering. I'm seeing the videos, and then I'm preparing very shortly. But I can't able to find the time to enter the problem solving session before.
Okay,
Mm.
okay. From where you are doing PhD?
I'm doing in MDT Hindu College, the MDT Hindu College, Tirunelveli, Tamil Nadu.
Okay.
Research Center. Yes, sir.
It's a CSIR.
No, sir, I am doing full time, but it is a research center. It
Okay.
is not come under CSIR. I am doing full time. No, I didn't complete that JRF and I didn't enter into CSIR.
Hmm. Okay. So
So the
it's,
formula, may I recollect? I think the formula it was in the assignment. It is an
yeah, it
assignment
was
10.
given. I think that I have gave that time, and that slide I think I have wrote, because this is the already prepared slide. So that time actually I
Okay.
have discussed. So just go through that recorded video that
Yeah,
will
how
be.
the same question you are showing that one. 1.49 kilo electron volt. That one we can divide it by. Okay, dividing. Okay,
So there
then
will be
but
around 390 electron volt pair around like that.
okay. But why we are adding that one with 1000? So
That is there. Do you know that that is a recording signal that you are getting, right?
yes,
There you
sir.
can easily see all the numericals that I have discussed.
Okay, okay,
Okay. Yeah.
okay, sir.
Simple.
Okay, continue.
So there is not so much. This is just the theoretical more or like theoretical. There are just 2-3 basics, not 2-3, just like 7 to 8 problems are could be there. How many marks would exams would be there? What is the
Sir, I think it
maximum?
will be for 100, sir.
100.
100, then it will be converted into 75.
Oh, okay, okay. Then I think most of the question would be easy because I think mostly question would be if there is like a objective 1 or 2 marks, not more than that.
Yes, sir. 50 questions will be there.
So
I
have
think
you made any kind of a notes for your study?
So, I think I was preparing the assignment solution only because I couldn't find time. Assignment solution, what was released in that mail. That's why.
Okay, but you have to be prepared. If you're doing it like uh, on a like for your credit transfer, then you have to score, right?
Yes, sir.
Are you doing it for your credit transfer?
Sorry, I couldn't understand.
Are you doing it for your credit transfer?
No, no, sir. Because I'm not a faculty. I'm not trying. I'm not trying. But
whether it is part
this
of
is the
your
first time.
coursework.
Huh?
No, no, no. I'm not doing it for my
Okay,
coursework.
okay.
Yes, sir.
Okay,
I am doing an PhD in physics.
okay.
That's why I want to know all the details under the material characterization, exercise, and time.
Okay, okay. So this kind of a question is very important that they can ask about the atomic scattering factor or the structure factor. So this I have discussed for all kind of systems like your SCC, BCC, and FCC. So this is like for your SCC and how can you calculate the total number of atoms like your 8 into 1 by 8, and then you have to put in this formula, and there from there you will get your intensity factor. Okay, this also we have discussed in our class. This was a very basic like a base centered and like your for your base centers a number of atoms and how you will calculate the intensity, whether it is odd or even. So this is all have discussed very thoroughly in the class. I think when you will watch this lectures recorded, then you would be easily able to understand about this base centered, FCC, and the BCC. These are very uh, simple concepts. Yeah, this is again the same thing. Like this can be asked. This is very well popular concepts. Yeah, there is an NaCl. We have also discussed how the Na and the Cls are arranged. What are the positions of these atoms, and multiplicity factor also like this for a 100 plane of a cubic crystal is 6, and for 11 plane it is 8, and how we have also already discussed it. So these are some very basic concepts that you just have to go through the lectures. Temperature factors, yes, how when you will increase or decrease the temperature, then how your atomic arrangements will differ. So here the intensities of the diffraction line decreases when the intensity of the background scattering between line increases, yes. And also there is a temperature. So here the reinforcement becomes more imperfect as the ratio of your mu by d increases. So that is nothing but as increase temperature will increase. So yeah, so there in the last we have discussed not very much, just basics about the temperature and some absorption factor. Not so
Sir,
very.
just sorry to interrupt. The previous question, what she asked, no, sir.
Huh?
I think that we have to simply divide it by the 3.8 electron volt.
Yes, yes, yes. That you have to divide simply, and I do not know they can change the number of the given what they have given like that. So I think in the question which I covered around 1.4 something was given, and 390 electron hole pair we
Yes, sir.
have calculated,
Correct, sir.
right? So, like in the XRD, like you all are like doing some PhD, so you must know the XRD. So, like for the crystalline materials, how your XRD peak should come for your liquid or the gases. So, this all we have discussed. Then why it is coming also because of there is a different grain boundary in your material that will cause giving a this kind of a sharp peaks, because it's also one kind of a defect because of the red arrangements of your atoms. In the gaseous it is different, in liquid it is different, in the crystalline or in the solid sample it is different. And then the full width half maxima, we have also discussed that what is the full width half maxima, and it is given, it is nothing, it is not a linear width, it is an angular width, so that's why it is given by your unit of angle or the degree or the radian. After that, we discuss about some monochromatic and the crystallized size effect, and how your dislocation or that there is a effect of your strain. Then there is a Scherer formula in your XRD. This you have to remember. So this can be used to calculate the crystallite size effect. T equals to zero point 0.9 lambda upon d cos theta b. So here they will give the lambda, d value, theta value, and then you can calculate the breadth b, and this is, I mean, you can calculate whatever they are given or whatever they are asking. It's just a simple formula. And then these are some locals, or I would rather say how your strain is affecting the peak shifting when there is no strain, no peak shift, when there is a uniform stem, where your peaks are shifting, it is to the right or the left, and when the strain is non-uniform, then whether the peak broadening is occurring or the peak shifting is occurring. So these are concepts that we have also
Sir,
touched upon.
here one doubt, sir. For compressive strain, it will be shifting towards right. Or
Yes, for the strain, when you will apply a uniform strain, your peak will shift. When you will apply a tensile strain, it will shift towards the left. But there is a non-uniform strain, there will be a peak broadening.
okay, sir.
Okay. Now, what can you get from your XRD? From your XRD, you can get different kinds of like a phase identification, crystal structure, lattice parameter, crystallite size, and endless. But what you can't get from here is nothing but your electronic state and the Fermi energy, because since one student is from physics background, so she must know the electronic state and the what is the Fermi energy, and definitely you can't get it from your XRD diffraction data, right? So these are some things, but there are some limitations that which you can't. And this is again about the XRD of a different samples like your gas.
Sir, can you previous question? Can you show?
This one.
No, sir. This XRD pattern of polycrystalline. Next slide.
Yeah. So crystalline material file contains a straight line with definite so broadened peaks, or the only one broaden, or the curved with a so it is asking about the polycrystalline. So polycrystalline is what you can easily see. Okay, it is a straight line with a definite spacing. It's not a when you will have some amorphous, then you will see some hump kind of a structure. Polycrystalline is what I mean. It is a arrangement of atoms. There you can see
That is
different sharp
correct, sir.
peaks.
Actually, I think the question it asked about JCPDS means ideal.
Yeah,
So I
that
think
is a
that
one
is why.
kind of a I would rather say a directory where you will you can find all kind of a you know
Okay.
crystal structure. So EBSD also we have studied that why it has used and what kind of information it will. So okay, this is some Kichuki pattern in the heart of your EBSD that is formed there, and this is your this is some basics about your EBSD setups, that how it usually looks. So these are the things that we have studied, and not so much to to see. You can easily give your exam. Just go through your video lectures, and I don't know whether like you guys have not made any notes, but it was I from the beginning of the day one or the class one. Those students who have attended my all the classes, you can ask them that I have always advised them to keep short notes, and while they were doing my classes, I have also um, letting them to prepare this assignments question. So if you have contact with anybody, you can go through their notes if they have. I mean, if you have not made, because you have a now very less time, and this time you can't make a new notes. You have to revise. This is the time of your revisions. Okay, so whatever you have studied, just revise. So that's why the students which have who have attended my classes, they all have a proper notes of my assignments, and I think the class notes, because I always encourage them to have proper notes, and I think some of them have followed very well if I know exactly, and also some questions I have discussed also. So I think that would be a very useful for them. So your exam is on 28, right?
29th, sir.
Oh,
Sunday.
29 Sunday. Okay. Yeah, so you have one full week, and in one full week you can see whatever you can do. At least target to.
Sure, sir. We'll try to, because
Oh,
I'm having 3 more courses, 3 more exam.
oh, you have three more.
Yes,
Oh
sir.
my.
So full.
Then you have to. Have you made any kind of a notes? No.
Yes, sir. Yes, sir. I've taken like some
Okay.
study. So the
Then
notes only now I have to revise, and maybe some numerical I have to practice.
yeah, yeah.
Then I'll go
Please
to
do
the.
that.
Okay.
Okay.
Okay, sir.
So I would not take much of your time because it's a very high time for you to practice and study.
Okay.
Okay.
Sir, may I know how much contribution from problem, sir? How much percentage will come from problem?
Yeah, actually, see, that is purely depend on the. I also do not know who is setting the questions. Is there a committee or some particular or the sir who has taught this course, or there is a panel? So see, these are some random questions. In fact, I do not know. You students will also not know that what would be the proportion like in your
Okay,
yeah. So you have to be ready for your each and everything like
okay, sir.
numerical as well as your theory, but this is mainly a theory kind of a course, so try to read more and more.
Then it will not be a
Yeah.
problem.
Yes,
Numerical also very straightforward only, sir. It's like
yeah,
we have
in
to simply
numerical is
substitute.
also they will give you all the cooked recipes, just you have to follow that, you have to put in the formula. So that's why I'm saying that even though if you will remember the formula, you must be able to solve the numericals.
Numericals,
Yes,
yes.
sir. Mainly we have to be careful with units and
Yes,
conversions. Yes.
yes.
Mm. Okay, sir. Thank you for suggestions.
Okay. So yeah,
Thank you,
see
sir.
you and
Thank
good
you
luck
for
for
your.
the exam. Okay,
Thank you, sir.
thank you.
You said not